Hey everybody, so today we have a lesson about some of the different crazy stuff that light does. And so my goal today is to just sort of give you a little overview, some of the crazy things that we can do with light. I'm sure you've had a chance to play with these if you've been in my class before. But the weird things that light does as we look through different types of material or as light travels through different things has a big effect on kind of what it looks like to us. So this little particular thing, these little glasses, called diffraction glasses or rainbow glasses. We'll talk about kind of how they work here. I also want to point out that I put this little video up here at the front, this little screenshot up here. I put some extra little videos up, little short ones that you can kind of watch as you want to. Light is pretty interesting, especially the phenomena that go along with light and how light behaves. It's so much a part of what we do and see and how we interpret our world, especially color and things like that. And it's very difficult for me to demonstrate in this particular format. So I threw a couple little quick videos up there. I'm going to strongly encourage you to take a look at them. It's not super required or anything like that, but they'll just give you a little bit more depth than what I can do in a couple minutes here online. So the idea about does gravity actually change color is kind of a fun one. So as you get closer to a black hole, would you get the Doppler effect? Would it change? So anyway, just a couple things to keep in mind as we get started here. Number one, as we're talking about light and we're talking about what light does and how light interacts with things, you got to kind of keep in mind that there's three basic things that light can do when it comes into contact with a medium or another, object, thing, whatever you want to call it. Number one, you can have light that can either bounce off of things, you can have light that travels through things, or you can have light that gets literally absorbed by things. And the fact of which one it does kind of makes a difference into how you perceive it. Sort of depends on where you are relative to where the object is. So for example, I have in front of me here a piece of green, it's like gel, like you'd use in a theater light, something along those lines. And so you can kind of see that it's obviously green. Well, what does this mean? Well, these things are green for two different reasons. Usually they are green because they are allowing certain colors of light to pass through. In this particular case, the only wavelengths that are making it to you through this are the green wavelengths. So that's transmission, that those lights that are coming through. Something like this looks green to you because, again, green light is being transmitted through, and then some green light's being reflected off of the outside. So we have a little kind of a couple of different ways that something can happen, as opposed to you take a look at something like this. You say, well, what is this thing? Well, it's just a green marker that I'll use later on today. And it's green simply because this particular part right here is reflecting green light to you. Other colors of light are being absorbed. It's kind of a weird process how this works. So when we see materials in our day, it's hard for us to imagine this invisible stuff, light, that is traveling through, bouncing off, and passing around all of these different objects. We got to try to keep those basic interactions in mind as we talk about these different things. So here is interaction number one. Interaction number one is something that's called polarization. And polarization is definitely one of the things that gives us, only works because light's actually a wave. It does not work, and it only works because light is actually a transverse wave. So there's a little added video that's on there that you should watch about how polarization works. But as a phenomenon, it's kind of cool. If you've heard of polarized sunglasses before, polarized glasses are really useful because they can block out uh, certain reflected types of light. So if you take a look at the pictures over here on the right side, the ones that are up here about like the view out the car window, these ones I'm referring to, when light bounces off of surface and it reflects off of surface, if those surfaces are relatively flat, the ways that these lights bounce off get sort of paralleled. They get sort of organized. That the ones that are not bouncing off together sort of scatter off to the side, but the ones that bounce towards you off of a flat surface tend to be all sort of in line. And so what a polarizing filter like this one can do is a polarizing filter can sort of help sort this out. So polarizing filters don't look like much when I'm just holding it up to the screen there. You can see it's just sort of a gray. It doesn't really look like a whole lot when you look at it. But they can have some really interesting effects. And I'm going to kind of hold my phone up right here. So you can kind of see my phone screen. And I'm going to put one of the polarizing filters in front of it. That doesn't look like too much, right? Most of the light is still sort of passing through it. You can kind of see most that's on there. So what you can see the effect of polarizing is that if I put a second polarizing filter, if they're lined up in the same direction, the light passes through. But if I put these at right angles to one another, I effectively block all the light that's going through at the same time. So how does that work? So if you imagine that light is a sine wave, right? It's sort of wiggly like this. Well, some of the sine waves are, wiggly up and down this way. Some of them are wiggly this way. Some of them are wiggling this way. They're all sort of different directions. So a polarizer ends up putting like a sort of a grate to it, a filter in a sense, so that only the lines that are going parallel this way can fit through. If you've got light rays that are coming through this way, they end up getting blocked. And so if I have two sets of grids, right, if I have lines going through this way, they can pass on through in a polarizing filter. But if I have a filter that's lined up this way, if I have a second polarizing filter that's lined up that way, right, so they're at right angles to one another, then it effectively blocks all the light. So polarizing is a way, it's part of the wave nature of light. It has to do with the fact that light is a transverse wave, and it has a way of sorting it out. So I really strongly encourage you to view one of the little videos about polarizing. Guy's kind of a goofy dork, but he's got a great little video of how you use a slinky basically to demonstrate what polarization is. So again, it's a really useful thing. We use a lot of times in filters and lenses to block out reflected rays. Those reflected rays, by the way, we call them glare. Glare is when you're getting reflected rays all coming through so you can't see what's there underneath. So like the picture on the left of the water, that's a nice Tahoe picture there, right? Where on the left, you see the glare bouncing off of the surface of the water and all those light rays are coming back to us. But if we rotate a particular polarizing filter just right, we can knock off that glare and then you can see the light rays that are penetrating through. So again, polarization is one of the things that light can do. It has to do with the wave nature of light and how light rays can be organized. A second thing has to do with how light starts to interact with boundaries and things like that. So number one, anytime you have a wave coming into contact with a boundary, it will reflect. That's the left side of this image that's on your screen right here. A lot of the light rays are or in this case, it's water waves, but it does the same thing for us. But you've got right in the middle here is a little water wave generator that's actually making these little circular rays, waves of light, waves of water, light's passing through it. So we're seeing the reflection on the bottom of it. And so these waves are traveling through to this hole right here, and then they're bouncing back. And you can see the reflected rays because they're actually kind of this direction, right, as they're coming back. So you can see where those reflected rays are bouncing back. And as those incoming and outgoing reflected rays are bouncing off one another, you get interference. That's constructive and destructive interference. Some of these dark spots, you're getting some of that destruction. The bright spots, you're getting some construction where they're overlapping just right. So waves and troughs sort of overlapping one another in just the right way. And then you get this really weird thing that happens right here. This is the phenomenon of diffraction. And so this is sort of a new phenomenon we haven't talked about a whole bunch because it doesn't happen as much with sound as it does with light. But this turns out that when light rays travel through a narrow hole in a barrier, and you can see this is a pretty small hole here, that they will pass through and recurve as they pass through. They don't go through and say in a little straight line like this. This was actually one of the really important pieces of information that gave us a hint that light was acting like a ray, like a wave, as opposed to more like a particle. If light was acting like particles, you would not expect, if this was like a mist of light, little particles of light, you wouldn't expect to see light over here. You would expect these walls would block it. Imagine if this was like a spray paint, situation, and you had a little tiny hole here. That for the most part, the spray paint would only be in this little zone right through here if it was passing through like a particle. Unfortunately, or fortunately, we know that as it passes through, it actually bends. And so we actually end up getting light all the way around these corners. This is why shadows don't actually have sharp edges to them. If you've ever seen something with a bright light that's shining upon it, the edges of the shadow are not perfectly crisp because, again, the light is bending around the edges of those barriers. And again, this thing is called diffraction. So I've got a couple of little demos of diffraction that aren't going to work great, but I do have a couple of little demos of diffraction. So these little things, again, are diffraction gratings. So when I look through these, I see rainbows because what this thing does is it's taking light from a source like my camera here, and it's causing it, let's see if I can get this to angle up just right. I don't know that I will be able to get it to spread. I practiced this earlier, and of course now will I be able to get the angles right. But you can eventually, if I do it right, get all of the different, I'm not going to bother with it. You're going to get all the different light rays to pass through. There's another way that we can see this, and it's an easier way to see it with lasers. So this is one of those little pen lasers that doesn't do a whole lot other than make a little bright red light. So you can probably kind of see the little red light that's on there. When I put this bright red light by the diffraction grating, you can see potentially that there's a whole bunch of different lights that are being shined through there. I also have a green one This one's a little bit brighter, so it may be easier to see. There's my green laser. And when I put this diffraction grating on there, you might be able to see that there's a whole spectral pattern that comes up. And that's because what's happening is there's lots of little tiny microscopic holes in this material that the light's passing through, and it's spreading out. So this is affected by wavelength, and that's something that you should kind of pay attention to, the idea that diffraction is related to wavelength, and it's also related to the size of the hole. So the smaller the gap, the bigger the bend. And so what I've got right here is another little set of diffraction gratings, and there's 3 different ones in the same thing. So one's got 100 lines per millimeter, one's got 300 lines, and one's got 600 lines per millimeter. So 600 lines per millimeter has the most bending to it. So when you do 100 lines per millimeter, and I shine this through here, I'm getting lots of little holes. As opposed to 600, they're bending even further, so I see fewer of them. And then if I do this one, they're even further apart. So again, it's not, but behind me, I know you can't see a whole lot, but one of the things to pay attention to in the lab simulation is that concept that the more the holes are, the more the bigger bend is. With the 600, the reason why we couldn't see as many holes on the screen behind me is because the gaps between the holes were quite a bit further. So the dots were just further apart. I could actually see them all the way around my room here. So again, more gaps, more bending. So again, this process is called diffraction. Key idea, bending of light rays as they pass through a barrier, a hole in a barrier, or around the edge of a barrier. So that's the concept of diffraction. A couple of physical examples of it, just in case you haven't seen it before. This is what diffraction looks like when you can kind of see it. So up here, you can see sorry, move this over the side. There's a seawall right here, and you can see the water waves are coming in, and they're causing this bending sort of pattern as they go around that single barrier. Same thing right here. It's actually bending around both ends of the ship. You've got waves coming in from the bottom, and then if you look around the corner, this is one of those giant oil tankers, by the way, you can see there's a curved set of waves bending around the left side, curved set of waves bending around the right side. Again, diffraction is the bending of waves around a barrier or between a little hole in a barrier. Next phenomenon is something called refraction. Now, refraction is the bending of waves as they pass through different media, okay? Diffraction is around a barrier. It's not going through the barrier, it's going around it. Refraction is going through it. And there's lots of funky little optical illusions that happen as a result of it. I've got a couple examples on the screen here. As light travels through different media, like water versus air or glass, it can slow down the light waves, and that can be enough just to cause them to bend. And all the different things that are happening on the screen here are because the light waves are bending, and that because they're bending, we see these things that look kind of funny. Like you can see even on my glasses right here on this side of my face, you can actually see kind of like the phenomenon that's in the picture, where it looks like my face is way narrower through my glasses than it looks outside my glasses. And that's because my glasses are so thick and they bend the light rays so much that there's an intense amount of refraction that's happening through my glasses. I like the physics is fun where he's sitting over here and it looks like his head is literally like next to his body, or you've probably seen this at home where it looks like a straw sort of bent. And again, it's because the light rays are traveling at a different speed through air than they are through glass, than they are through water. And this causes these interesting little phenomena. So again, diffraction is around a barrier. Refraction is through a material. We'll do refraction a bunch more when we get to the chapter that's on lenses. Refraction also causes the Pink Floyd phenomenon. Refraction, when you pass light waves through prisms, you can actually also get bending, because refraction not only affects the medium and how fast it's traveling, but it really does affect the wavelengths of light, that different wavelengths of light bend more or less depending on what they are. So you can kind of see in the Pink Floyd phenomenon here that the blue and violet sides bend quite a bit more than the red and yellow. So the short wavelength light gets bent a lot more than the long wavelength light, which tends to travel in more of a straight line edge. And so this is going to get us in the phenomenon of dealing with color and how we can actually see color and separate it out. So again, refraction, bending through a material. So when we are dealing with colors of light, there's an important thing that you do need to know about it from a physics standpoint, is that color in physics is very different than color as you're used to. Color addition in physics is not the same as color addition of crayons. It is absolutely 100% weird. So I would suggest again that you watch one of the little videos that's on there, the additional ones showing this. But with light, if you actually get really close to a screen, like even an LCD screen, an old TV screen, you'll really see that there's 3 primary colors of light. They're red, green, and blue. Those are the 3 primary colors of light. Now we're talking about light production, not crayons or paint. I know the primary colors of paint are different because paint is a pigmented surface that's absorbing and reflecting colors of light. When I'm talking about this sort of stuff, this is actually production. The actual light rays themselves are red or green or blue. Those are the primary colors. And when we add them together, we get some really interesting pairs. So like when you shine red and green light rays together, your brain interprets that as being yellow. So literally when your brain receives red and green waves at the same time, your brain goes, oh, look, it's a yellow color. When you take green and blue and add them together, when you receive both of those colors of light, your brain interprets it as this light color, which is called cyan, C-Y-A-N. And cyan is a kind of a sky blue color. And when you see red and blue rays at the same time, your brain interprets that color is known as magenta. It's kind of that hot pinkish purple kind of color. Again, this is addition of light, and this is what I want you to learn because we are not in kindergarten learning how to mix our paints. But what you'll find is that the addition of paint and the addition of light are very, very different processes. Paint works on absorption, subtraction, as opposed to light works on the concept of addition. So with pigments and paints, you can kind of see how this works with these little examples that are on here. Again, light is the color. Pigments either absorb or reflect those colors. So when you have a red object, or like I showed up that marker that was earlier, but when you have a red object like this red pen, what's happening is white light is striking it, which contains all the different colors of light. And this red material on here is only reflecting red. So your eyes, when you look at this, is only receiving the red rays that are hitting this and bouncing off and back to you, as opposed to the green and the blue. And I'm referring to that little screen up here. I don't know if I can get it. This image up here, right? If you're talking about that one right there, the only colors of light, hold on if I can get that to go, whatever. The red is bouncing off, but the green and the blue is being absorbed by this and not reflected. As opposed to if I have a blue pen like this one, and this blue marker right here, the reason why you see it as being blue is because it's bouncing blue light rays are bouncing off, hitting this, and then bouncing back to you. The red and the green light rays are being absorbed by this. So again, that's how you perceive an object as being colored, which is different than perceiving light as being colored. They're very different. And again, when we talk about the secondary colors of paint, of pigment, there's cyan, magenta, and yellow. By the way, those secondary colors are the colors of printer ink. And that's how you actually get certain different colors to print perfectly by absorbing only certain wavelengths of light and reflecting pure colors. So this has some interesting phenomena when you actually take a look at colored objects under different colors of light. And I'm going to challenge you guys. A lot of you have those color changing LEDs in your house. I've seen you. And so it'd be really interesting for you to go and document some of that. So like if you take an apple that's red and you show it under red light, you'll see one particular thing. If you take the apple and you look at it under a different color light, then you're going to see some different colors. So I'll show you what this looks like here in just a second. So again, addition versus subtraction of light. You get to see some really weird looking processes as you do this. So on the screen right there, I know you can kind of see all those different images, that when you have colored objects and you view them under colored light, now you're getting the interplay of addition of light and subtraction of light. The objects themselves are subtracting light. They're absorbing certain colors and only reflecting certain colors, and you only see the reflected objects. So I'm going to see if I can show you a really funky example real quick. So take a look at the image of me and not necessarily the image that's the big image that's on the screen. So you can kind of see right here, I've got three words here, blue, red, and green. Here's what they look like when you start to absorb them through different colored filters. So when I put a green filter in front of my camera, you can see that those colors look really different because the green is only allowing certain colors of light, green light, to transmit through it. And so certain lights are bouncing back in a real particular way. Again, it looks really funky when you do that now. Looks, your color vision starts to readjust, right? Here's a blue filter. And so you can kind of see that it washes out because, again, the blue filter is only allowing blue rays to transmit. And there's nothing like the word red. The word red can't reflect back blue light. So it essentially looks black. And then here's a last one, a real quick example, and then we are done for today. So here's a red filter. Again, this looks really strange. Let's see if I can kind of adjust a little bit to get it to work a little bit better. But with this, the red filter only allows red light to go through, which is sort of interesting. And the blue and the green you can see, but the red one completely disappears. It's really, really weird to look through a red filter. If you get a chance to do this at your house, take some red plastic and look through it. It'll definitely mess you up. So there you go. Some different phenomenon of light that we're talking about. So there's polarization of light, which has to do with the fact that light is a ray and whether it can pass through different types of materials, whether it's all oriented this way or all oriented this way, or you block it all together. You've got reflection and interference, which we've talked about plenty before. You've got diffraction, which is the spreading of light as it passes around a barrier. So either bends around corners or bends through a little tiny gap and then recurves as it bends through there. Then you've got refraction, which is the bending of light as it travels through different media like air and glass and water. And then that refraction also leads us into that idea of color, is that when you actually bend light through a crystal or something like that, and you see all the colors in white light, all of those colors are there. It's only when we refract them that we can kind of spread them apart and see the different component colors of light. And that kind of leads us a little bit into color theory to kind of see that idea of transmitting colored light, production of light versus absorbing light and reflecting light. So I know this is definitely a very brief overview. We'll talk a lot more about color vision in our Zoom meeting this week or our online, in-person meeting. So there you go. Hope you enjoyed that. A little introduction to some of the behavior and phenomena of light. I hope you had fun, and I'll see you soon.